So let's first review the last few topics that we have discussed. They're all interlinked. But the last one, the really very last one topic was very central, and I have been talking about that so many times. So and finally we proved that indeed the direction of the gradient is the direction of the fastest growth of the function of whatever number of variables. So we figured out what that means to begin with, and the mean means is either you think in the most basic way as the parametric curve going a straight line going in that direction, and then you just evaluate its composition with the function itself, or there is a special term for it that is called the directional derivative. So bigger result that we got from it is illustrated at the bottom. It is the different directions that you can go from that given point, and then they all compare to the gradient, and depending on the angle, because directions are determined by unit vector, so it doesn't really matter what the magnitude is. So they all compare to the direction of the gradient vector. And then in there it tells you everything you need to know about that particular point and how the function behaves there. I'm talking about function of 2 or 3 or more variables. So as you can see, if you go in the direction with the gradient vector, then you will have the fastest growth. If you go in the opposite, you will have the fastest decline. Okay, in the opposite direction, that over there are the purple one, and then everything is in between, left, right, and there's certainly it's missing here, and that is the direction of which is perpendicular to the gradient. And that is the direction of what?
A B?
Of what?
A B?
Yeah, but they all are. Oh. So I show you the spectrum. Yeah. And so the two special cases are with the gradient, against the gradient, the fastest and slowest growth, and the perpendicular to the gradient, what's the growth? 0, right? So because we go, essentially this one is parallel to the level curve. Okay, so that is a big deal, and all applicable to high dimensions, except instead of level curve, then you'll have a level surface and so on. So actually, it's probably a good idea to actually imagine that when that level curve is a surface, or if you zoom in, it is a plane. But the rest remains the same, so this will be my vector of the gradient. So this being my point A over here, point A. Okay, and then once again the opposite direction is the direction of the slowest growth. And then once again all of the vectors on the plane, so all of the in many directions will be perpendicular to the gradient, and they will be all at the same time there. As such, they will be tangent to the level surface. Okay. Okay. So another topic we finished just recently was the topic of gradient test, the gradient test right here, the gradient test to whether or not a given vector field is the gradient of some function of 2 or the other one 3 variables. Okay, so the conclusion was not the conclusion, but rather the test was the equation here for dimension 2, and the other equation is 3 equations for dimension 4. Okay, so first dimension 1. Dimension 2, rather. So this might be over here. Okay, so as you can see, the first component of the vector field P differentiated with respect to the second variable is equal to, has to be equal to the derivative of the second component of the vector field differentiated with respect to the first variable. Okay, dp dy is dq dx. Okay, so p once again is the component, the x component of the vector field. Okay, so then if it is not satisfied that identity, then it is not a gradient vector field. Otherwise, it just fails. We cannot say anything. But at least for the near future, I want to use this and define a concept that is actually measures how close the vector field is to being gradient. And that is simply the difference of these two. It is called the rotor of the vector field, and it is the difference of these two, dq dx minus dp dy, right? So if the vector field is gradient, then the rotor is 0, and the rotor is certainly what indicates to what we have been talking about, rotation. Is there a rotation of the vector field there or not? If it is equal to 0, it's called irrotational, and well, appropriately, and then we'll see if it is really true shortly. So as you can see, what is the nature of the rotor? Out of all the functions that we know, what kind of functions?
Oh, it's a real value function.
Yeah, of two variables, yes. A function of two variables, because P and Q are functions of two variables. You differentiate them partially, producing two more functions of two variables, and so it's just a function of two variables. So you can just plot it if you like, and then you will know wherever you that function is equal to 0, not equal to 0. You will see it immediately. Now it's more complicated with dimension 3, and you can imagine what happens in high dimensions. But in dimension 3, as you can see, we have 3 identities, okay? And then we want to have a similar thing established. The concept is called curl, except since we have 3 identities, and we want to have a similar situation that when that curl, whatever that is equal to 0, then all of these 3 identities are satisfied. So in other words, I will be looking at dp dy minus, well, in some order, I probably will try to ignore this as much as possible, in the sense that the signs might be non-standard. So I'm just copying things so there will be no doubt what I'm talking about. Okay, so these 3 quantities would have to be equal to 0 in order for us to pass the test of gradient test. So how do we do it? 3 quantities, well, with one quantity that embraces them all, and the answer is we form a vector. We form a vector, or in other words, it is going to be a vector field. So vector field with 3 components, computed in this fashion, and then you just have to assign I, j, and k, those basis vectors in 3D, to these coefficients will be of those. So if I had to do that, I would do this, and then I would put, where would I put it? I would assign it to the missing variable. So this is x and y. Okay, so I'll put the third one, k. Okay, and then z and x, it gives me y. So this is j, and then the last one is I. Okay, so that will be the curl with some signs. The signs we'll have to work out later when time comes. I just want to see where it all comes from. So it comes from the idea of the gradient vector field. Gradient vector field, all of these identities, you should remember, come from Claudeur's theorem, and from the, in other words, from mixed derivatives being equal to each other. Remember, there you see those arches, they are actually equal signs, and they come from that theorem. Okay, so we'll we'll go back to that when we discuss rotation again. and to evaluate, once again, to evaluate how close a vector field is to irrotational one. Okay, so now there are also the topic that came up, well, that started, and this is the start of the topic that we're gonna spend some time doing in line integrals. The one that we have discussed was really very familiar to what we discussed early on. It's because it doesn't rely in any way on neither function of several variables. Well, it definitely doesn't rely, it doesn't have any use for the vector fields. Okay, so it is the idea of arc length interval that is almost identical to the one that we saw in the beginning when we evaluated the arc length of a parametric curve. Okay, so as you can see, that part is all familiar except the extra term that we now use. This was the extra term that we had. The rest is the same. Okay, so this is all the same. Same as before. So the difference is certainly familiar when you do compute early on in calculus 2, you compute the area or area, and then what if you have a variable, you have a region, you can compute its area, right? But what if it is we're interested in the mass of that object, and then there is a distribution of weight in it, the density varies. So then instead of just taking up an integral of that object, double integral ultimately, you integrate that density. Density is to be integrated in order to get mass. When density is constant, then we're integrating pretty much nothing. So this is a similar situation, but ultimately the end result is nothing but an integral of calculus 1. So look at it. It's not double, triple integral. It's a single integral. So that's why we're not going to spend a lot of time on this. The only thing that we need to mention is the notation. And the notation is integral C F ds. Okay. So C is a curve, or it is the path of well, let's just say it's a curve. Is a curve. So this is actually a starting point rather than the end point of the whole thing. So there is a curve, and then we want to compute a curve on the plane, like this, on the plane with variable density, and in this, and we cut out that curve from that plane, and then we end up with a piece of wire with variable density, and we want to know its mass, and that's how we would find it by this kind of integral. Step number 1 is actually parameterize C, and that's where parametric currents come from, and then that's how we convert that's how we understand this notation. This is nothing but notation. So now there is no unspecified curve, whereas this curve is specified, but parameterization is not. It is when you do parameterize it over there, that function f, then your integral turns into that integral, which is familiar integral. Really, all you have to do is just to compute the derivative of the parametric curve and then plug it into this formula. So computationally, this is the way of compute it, and I guess this is the better, but this is the notation and the definition. What is the meaning of the line integral of f, a function of several variables, along a curve C? Okay, they certainly match in dimension. So if the function is of 2 variables, then the curve is on the plane, and so on. As you can see, you can see that, first of all, you remember where ds comes from? Why ds?
Is it the arc length?
It is we're referring to the arc length. If it is then if you choose from the beginning, you choose a parameterization that is arc length parameterization, then that this part over here will disappear, and you have a very simple integral of simply of the composition of the two functions. If not, you in a way what you do is well, you don't really need it. Any parameterization would do, except well, you have to it has to be a regular parameterization of C. Remember what it means. It means that it is, well, first of all, it's certainly continuous, and secondly, the derivative is not equal to 0. The derivative equal to 0 is always a problem in solving problems like this, because it might indicate that you turned around and go back. You're trying to compute the length of a curve, and yet you've covered it many times. So that's why regular parameterization which is not as restrictive as the arc length parameterization. However, it's good enough for our purposes. Okay, so that, like I said, I will just refer you to like whatever it was in September or sometime in September when we talked about parametric curves specifically, as well as the arc length. Even though function f is certainly a function f lowercase, a function of several variables. But otherwise, it's just a substitution. Then after parameterization, all you have is a calculus 1 integral. Okay, so we are moving, however, in a different towards different line integrals, and that is they're pretty much referred to as work. So work as a line integral. Okay, so we start with a simple situation because the work has not been discussed. And so what are the participants here? The work, to begin with. Well, the work will be the outcome, but the work of what? Of a force. Okay? I guess I'll call it that way. Okay, the line integral, it means that this is a line. What that line refers to is the path. So we're moving along a path through a force, through a force field, such as gravitational field or any kind of other field that we can imagine. We're moving through it, and then we determine how much work either we are doing against that force, or the commonly in physics it's referred to as the force working. So doing some work for us or against us. Okay, if we're moving through gravity, if we're lifting something, then the gravity, we are working against the force, and at the same time the work, you can say that the force has performed some work. Okay, so that's what this is. So path to begin with, and then there are vectors all over the place. Okay, so before we do that, let's start as always with the simplest situation, just to refresh your memory about the physics of what's going on here, and then before we go take it all the way to the most general case, a force field and a path through it. So just to explain why things are the way they are, so we start with dimension 1, and moving, say, horizontally, and well, there is a definition for it. So where the work is, what is the work? In the one-dimensional case, we are moving horizontally, and the force is, say, so this is our path, or in fact not even the path, it's just a, well, let's say a path, and then there's a force. So what's remember what's the meaning of the work?
Force times distance.
What?
Force times distance.
Force times distance. Force times distance. And the only thing we're already familiar with some of the issues, and they occur in a one-dimensional case. And that issue is that we encounter when we study motion. This is really not about motion, as you can see, but the issue is what we talk about the distance. We have replaced the word distance with something else. Displacement, because we can move back and forth, and it matters. So if you go with the force, against the force, the result is the exact opposite. So displacement. So if this is the path, displacement, then so we're already talking about vectors. Even in one-dimensional case, studying vectors is using vectors still makes sense, even though you can replace them with simply numbers that are chosen to begin with from the beginning to be algebraic, positive or negative. Okay, but then you have to decide whether or not your distance that you have covered is, you don't want to do this distance, you cover distance along the force, that's one thing, and then against the force is different. We know how to, you don't want to do that, especially when in the future we will be changing directions. So once and for all, you actually talk about displacement as a vector, and so initial location, final location minus initial location is your displacement. Okay. So just like in motion, when you start studying one-dimensional motion. Okay, so force times displacement, that the force still remains. So it's if everything is constant, this is what we're looking at. The force, it's the same force. Okay, so so the why it makes sense is apart. In addition to taking care of the directions, displacement and force have directions, and we are taking care of that. Even though certainly it certainly starts with the right way to start would be to have the x-axis. If you do in one-dimensional case, then the x-axis is tells you to begin with whether or not the force is positive or negative, and the displacement is positive or negative depending on how you move. How they are relative to the direction of the x-axis. Beyond that, that's not going to work as much in high dimensions, but it's still worthwhile. So it's literally could be 3 times 2 is equal to 6. That could be a computation of the work. So you moved by the whatever units. I don't want to go into the units really, but you can imagine that 3 units of force. And 2 units of displacement give you 6 units of work. Okay, now in dimension 2 it's more complicated because the moving against, there are all those intermediate possibilities between with the force or against the force. There are all other possibilities. So if I still have my force pointed this way, so I still can go with the force. So with the force, and then I could go, that's displacement, and I could go against the force. And what else is left is everything else. So all the other possibilities, you can go up and down. So all of these are also possible. So all of these are displacement. Even if you imagine, let's imagine for now that the force is fixed, then all the possibilities of which way we could move is infinite. So these are possible displacements. Okay. Okay. Then the question becomes, how do we arrange in such a way that the algebra takes care of everything just as it did here, right? So positive, negative taken care of by the nature of the quantities that we chose to be for those 2 quantities. Algebraic numbers, positive or negative, comes from the beginning. You know what they are. Okay. Similar situation is here, but we know that we're not going to multiply vectors as easily. But the answer is certainly is predictable. So force is F is a force, but it is a vector. And displacements are also vectors. Okay, and then as you can see, the multiplication of vectors then would be an issue. And what kind of multiplication do we? The only kind that we know. What kind of? How do we multiply?
The dot product?
The dot product. Okay, and E, and the it makes sense to begin with that first of all vector times vector. Okay, that makes sense. Secondly, remember the outcome of the dot product is a scalar, which makes sense about the work. So even though the quantity depends on the on the whole setup, which way you go, but the outcome is a number. How hard you have worked is not really is not the vector quantity for sure. So it is a scalar that works out too. So well, at least we're moving in the right direction. But there is certainly an explanation why it is supposed to be the dot product is it comes from where's mine? So let me call it D for the time being. So I'm talking about the F times D. So why the meaning of F times D is a dot product. It is I invoke this formula again. So alpha, the angle between F and D. So why does it make sense? In fact, we could have probably started with the analysis of the meaning of the force and how we can decompose our displacement. We decompose the displacement. I would say instead of how about we decompose the force relative to our displacement rather than vice versa. So suppose this is our displacement of F. No, that's a D. It's our D over here. So we're moving in that direction, and my force is pointing in this direction. Then, as you can see, part of the force does not work against us. We only care when we're going against, we're pulling against gravity. So I'm lifting. That certainly takes some work. But if I do it diagonally like this, then the horizontal motion presumably has nothing to do with gravity. So this part is lost. I am not spending any effort in that sense, or certainly the gravity does not do anything to the action if I'm moving horizontally. So if I'm moving diagonally, then the raise that I do, I'm raising the object, and then so if it is diagonal, then this part is relevant. This is irrelevant. So that's what I do here. Irrelevant. Then the relevant part will be this. So this is relevant. Relevant part of force. Okay, and then perpendicular part will be irrelevant. So let me put it in red. This is the important part, and then the part that we quite literally throw out is this one. So say we have well there's sometimes this is how it's written as decomposition relative to a particular vector. So perpendicular part in the parallel part or collinear part. So then this is F parallel. So parallel to D, that is, and the other one is the other one, I suppose, F perpendicular. So the perpendicular is irrelevant for this particular application. Okay, so and then how do we find this F collinear part? It is based on the angle alpha, and it is in fact equal to what?
It's the projection of F onto D?
It is the projection, and the formula is a projection on D and it is equal to the magnitude of f times cosine of angle. Okay, so that we take with what's relevant, we throw out the rest, and that's how the dot product works. So it gives us the algebraic way to express projections, pretty much. The geometry behind the algebra of the dot product is the projections. So as you can see, it's also entirely independent of the coordinate system if we were to choose. Okay, so all right, so then that's the answer. So the work is W is equal to F times D dot product. So this is pretty much the definition, as simple as it gets, simply the dot product. And where we know what the challenge is going to be is what for both of them variable. Both the direction of our displacement as well as the force are variable. But before we do that, let's see how far we can get with this, and we can get fairly far. So, for example, that picture is quite clear. But what if I travel? So F is still fixed. The force is still fixed, one vector, but my travel varies like this. So suppose my path is made of straight edge segments. Okay, so you can think of it as a sequence of points in, say, R2. Okay, so how do I compute the work?
We're just going to do it component by component and sum them?
Yeah, item by item, I will the formula that will apply. So it will be just add them. So it will be, what is it? It will be like F is the same dot D1, F D2, F Dn. Okay, so if this is D1, D2, so these are displacements. And you probably realize that whenever we talk about displacement, it is a difference of two locations. So it is if I describe my motion not by displacements, which you have to measure afterwards, but rather describe them in terms of a parametric curve. So whether it goes straight or it goes curvy, it doesn't matter. So suppose this is what is I'm referring to is x equal f of t. So our motion is described by this curve, and that's a parametric curve. Okay, and then suppose I am at this location at time t naught. This is t1, this is t2, t3, t4. Okay, so these are my intermediate stops. And then then how do I compute displacement? I just simply subtract. So I'm going to have f times f of what is it, t1 minus f of t0, okay, plus f dot f of t2 minus f of t. I have too many f's. Okay, how about p? So parametric curve p. T1, and so on up to the nth, which is f dot p of tn minus p of tn minus 1. So these are how we compute the displacement, simply the differences. And okay, you certainly can see where we're going with this. At some point, we're gonna have a summation. We're gonna have even sums. And you can probably guess every time you see differences, it's probably an indication that there will be differentiation at some point. But at this point, it's just an example, so you can see how we can simplify this. And what is the answer? If I simplify this, what do I get?
Does it telescopes to ft n minus 1 or ft n? minus,
F of P Tn Tn minus the total displacement. Okay, so all of these will cancel. All of these will cancel. Okay, so then the end result is then dot product of my constant force with the total displacement. So the total displacement I'm referring to is this. This one. Okay, so why so easy? It is because the force is constant. You can imagine if the force had been changing as we move along, the cancellation becomes impossible, and that really indicates that not only the path matters, so how you get from point A to point B matters. So this is say point A, point B. When the force is constant, such as gravitation close to the surface of the Earth, then it is called the path independence. You will arrive to the destination. You will spend as much force no matter what path you take. Okay, so I took this one. I could have gone straight. The answer would have been the same. So that's a simple example of when things work out easily. But one of the questions will be when do they work out this way in general? And you might try to guess under what circumstances more complex than just constant vector field, the path doesn't matter.
oh, if the magnitude of the force is the same everywhere?
No, it's not enough for the magnitude to be constant. We will not be able to factor it out in this manner if it is rotating. And that's I guess that's what I'm driving at, is that when the vector field is not only, when it's constant, everything works out. When else why doesn't it work out? It is when the circular path brings you back with and you expend some force. Okay, so you can imagine that here, so with all this path available, suppose I go from point A to point A, making full circle. What's the effect of that? Like this. So suppose hypothetically this is my path. What's the work?
0.
The work is 0, right? So that's the path independence. The metaphor I can think of is so well you know that joke that the parents telling kids how when they went to school they had to walk 5 miles to school. And what's the punchline?
Both ways.
Both ways, right? So that's not the case. In other words, it's certainly possible to walk from point A to point B uphill both ways, but there is a bigger point there. What if you are making a circular trip? Can you, and come home, can you walk uphill all the way? It's still impossible, right? So it's really not the part of the joke that you're moving backwards exactly the same road and presumably, and then you're walking uphill. But the thing is, you cannot even imagine that a trip that ends at the same spot with the and you're walking uphill all the time. So then the relevance here is that if you walk uphill both ways, it means that you work against the gravity of the whole trip, which is once again is impossible. And it's not necessarily just because it's not constant, but rather it is the nature of the force, which is we already talked about. We call it gradient vector field. We call it conservative vector field. Because you can imagine the situation that is well, let's modify this joke a little bit. So is it possible to walk to school against the wind and then back also against the wind?
You could.
Even if we imagine that there is no change in the pattern of the wind is exactly the same. So if that's the case, if you go back and forth, then you certainly go with the wind, against the wind, it cancels out. But you can imagine that if you make a round trip, it is possible to walk against the wind all the circular trip. Okay, so why? Oh, that's the difference between the force that's produced by the wind and the one that's produced by gravity. So gravity, whether it is entirely constant or not, will have this property of being gradient vector field that is it make it impossible for our trip to be to have expand a positive work on a round trip. So on a round trip, when the force is constant or otherwise gradient, we cannot expand positive amount of force, positive amount of work. But if it is for other kinds of non-gradient vector fields, it is possible to make a round trip and expand on net positive amount of work. Okay, so that's the crucial difference. That's why we spend so much effort on it. And then the main difference is once again gravity. And I'm talking about gravity. This certainly is an idea of gravity which is constant, which is the case next to the surface of the Earth. It is assumed to be constant. But imagine gravity that we have not demonstrated. But the gravitational vector field, if we take throughout the whole solar system, it's the same. It's still gradient, and it is. You cannot, once again, you cannot make a trip around it without cancellation. So the work on net will be zero if you make a trip not only around the surface of the Earth but also trip around the sun, I suppose. So that's the simplest situation, but and you can imagine how things become complicated once we make F here a vector field. That is the development that complicate things a lot. So F now is a vector field. Okay, so it's a vector field, and even if you took a straight trip through that vector field, it still won't, if it is a variable in any way, the complexity becomes obvious. So suppose this was our trip, and but as you can see, the vectors of the vector field are changing. So at every moment of time, we expanding different amount of work. Okay, you can, however, see that the whole story is more or less additive. All you have to do is just to split appropriately into smaller pieces. Split your trip into smaller pieces, and along each of these smaller pieces of your trip, you can assume that the vector field is constant, and then you just add up everything in the manner just we did over here. Okay, so that will allow us, at the very least, to carry out the computation in the at least compute the Riemann sum. We can use it to spreadsheet to compute work as well. So we proceed then to doing that, and as always, it starts with a partition. So suppose we have so x equal f of t is our path, or a primitive curve. Define a neutral AB. We always assume that they are continuous, so we don't have to jump. And so we have a partition, or a sample partition of AB. So we have x inequality from x0 to xn, which is B. Okay, and then we have a sample point. So these are the nodes of the partition, and then sample points are in between. So sample points, that's where our path will be sampled. So it will be C1 between x0 to x1, and then C2 between x1 x2, and so on. So it's really uncomplicated. It all kind of goes back to calculus 1. And so these points are inserted in order to sample our function. So, but we're not going to sample the function itself. Well, we're going to sample the function itself, but in addition, we will use that function, that sample function, in order to sample the vector field. So So the locations are f of t naught, f of t1. So they are on the plane or in space, f of tn. Okay, so all of these location, I'm sorry, these are C's. Sorry about that. These are C's, sample points. C1, C2, Cn. Okay, so these location in space, they are somehow we're moving somehow through our space, which could be 2 or 3 dimensional. And finally, and then we sample. So these are the sample locations, and forces. Forces are also sampled. Say, well, I'm doing it again. P, and another P. Okay. So forces, F of the vector field, so it will be F of P C1, F of P Cn. Okay, we'll finish it.